Look up your IP address, and there is a very good chance it's a fake. It's a temporary mask designed to hide your actual device. Because to survive, the modern internet had to learn how to lie to you. The architects who built the internet's foundation in the late 1970s used a system called IPv4. The math behind this architecture created a strict ceiling. It could only generate about 4.3 billion unique addresses. At the time, engineers distributed these addresses using a legacy hierarchy known as classful IP addressing. They grouped addresses by size, handing out massive blocks to single organizations. This chart shows exactly how allocations were split up. As you can see, 50% of the total address space was dedicated to Class A networks. This meant millions of IP addresses were locked up by a few large entities, sitting completely unused. The early network was essentially a private club for universities and military researchers. By baking such massive inefficiencies into its core structure, the system was mathematically destined to fail once it reached the general public. Then came the World Wide Web, quickly followed by the introduction of mobile phones and always-on smart devices. We rapidly hit a wall known as IPv4 exhaustion. The global demand for connected devices simply swallowed the remaining supply of those original 4.3 billion addresses. Without a unique IP address, a device cannot send or receive data. Hitting this mathematical limit meant that the entire physical expansion of global communications was about to stop cold. Shutting everything down to build a new network from scratch was impossible. Instead, engineers developed a series of invisible structural workarounds to keep the existing infrastructure alive. Before tackling the global IP shortage, engineers first had to fix a very localized problem: severe traffic jams occurring right inside office buildings and homes. When computers communicate on an Ethernet network, they frequently send out Layer 2 broadcasts. This is essentially a digital shout. When one machine needs to find a specific destination, it yells its request to every single device on that local network. Basic network switches blindly echo these shouts out of every port. If you connect too many devices together, the sheer volume of these continuous broadcast messages creates massive noise, slowing the entire network to a crawl. To stop this, networks rely on routers. Unlike switches, routers are programmed to ignore these local shouts. They refuse to forward broadcast frames, acting like soundproof walls to segment the network into smaller, quieter rooms. Network segmentation keeps individual devices from drowning in irrelevant chatter. It provides the exact structural control needed to manage massive scale. With the noise contained, administrators apply a process called subnetting. This is the practice of slicing up a large broadcast domain into smaller, highly efficient pieces. This diagram shows a single router carving up a network physically, distributing distinct IP blocks by geographic location. Each floor operates in isolation. The first floor gets its own dedicated address space, completely separated from the rest. This schematic shows how the exact same concept applies logically. A network can be divided by function, creating separate paths for engineering, marketing, or accounting, even if the computers for all three departments are plugged into the exact same physical switch. Subnetting cuts down unnecessary traffic and allows engineers to apply strict security rules to specific groups. It turns a chaotic web of wires into a tightly controlled environment. This strict local control set the stage for the ultimate workaround for the global IP shortage: private IP addresses. Organizations can freely assign these private IPs, like the familiar 192.168 block on your home router, to billions of internal devices. But there is a catch. These addresses are strictly non-routable on the global internet. If millions of people are using the exact same private IP address at home, how does your specific laptop actually retrieve a web page from a public server? This graphic shows the solution: Network Address Translation, or NAT. As a packet leaves your private network, the router intercepts it and physically translates your hidden private IP into a globally unique public IP before sending it out to the web. NAT operates like a digital bouncer. It hides billions of private devices behind a tiny handful of public-facing addresses, single-handedly keeping IPv4 functioning today. Every time you stream a video or send a message, your data is making a direct Unicast connection, actively navigating this massive maze of local subnets and NAT translations. Because true public IP addresses remain a finite, precious commodity, they require strict global governance. This is handled by the Internet Assigned Numbers Authority, or IANA. This map illustrates how IANA manages the remaining supply. They delegate blocks of IP addresses to exactly 5 regional Internet registries, based entirely on geographic need. The global Internet isn't an endless open frontier. It is heavily regulated real estate, meticulously partitioned and metered out by these 5 organizations. The early engineers originally envisioned a pristine, one-to-one mapped network where every computer had its own permanent public identifier. What we actually use is far more improvised. We operate inside a layered ecosystem entirely dependent on artificial segmentation, clever subnetting, and constant on-the-fly address translation. The fact that this patchwork architecture hasn't collapsed under the weight of billions of devices is an engineering marvel. It proves that a foundational system doesn't have to be mathematically perfect to connect the globe. It just has to be endlessly adaptable.